All right, let's have a look at level loops here. Now what a level loop is a type of control survey. What you're doing is you're starting at a point of known elevation, usually a benchmark of some type, and then you work your way around with your level and your rod and end up at a point of known elevation. In this case here, in this representation, we're working our way around from the benchmark 1 to turning point 1 to turning point 2, and then closing back to benchmark 1. So we're finding the elevations of turning points 1 and 2. This is a plan view. You might think of it as a bird's eye view representation where we're looking down on the loop. This is a handy way to draw them up when you start and end on the same benchmark, as you often do when you're in industry working. Now another way to draw them up is like this. This is what I call a profile view, which is kind of a cut through the ground as though you're standing there looking at someone surveying. This works better if you're starting and ending on different points. These would both be points of known elevation, benchmark M and benchmark R. And we're surveying our way down this valley and back up and starting at M here, and then we end up on R. Both M and R are points of known elevation that correlate to one another. So what we do here is we know the elevation of benchmark M, we put the rod on it and set up the level, look back on the rod, and we'll see an elevation, or a height, I guess I should say. And in this case, this example, it's 1.33. Well, what that means is the telescope is 1.33 feet above the benchmark. So we can take that benchmark elevation, add 1.33 to it, and we'll get the height of the instrument. All right, then now we know the height of the instrument. We can move the rod ahead and put it on the next point down the way, which we're calling turning point 1. We can again take a shot on the rod. Now, this point right here, being as this is a level and it shoots a level line, this point right here that I'm outlining, it would be the same elevation as the instrument because the instrument shoots a level line. So we could subtract off the reading on the rod from the HI, the height of the instrument, and that will get us the elevation of the point on the ground. We can just keep going with that procedure, taking a back sight on the benchmark, getting the HI, moving the rod ahead, taking a foresight, and getting the elevation of the point on the ground. Then we can pick up the instrument and move it ahead, look back on the rod, add that back sight to the elevation of the ground and get the height of the instrument, move the rod ahead, take a shot on the rod, and get the elevation of the ground. And we can just keep doing that procedure and link these elevations together as we go. All right, now you'll notice when we look back, we're adding the rod elevations. And so the back sights are sometimes called plus sights because you always look back and add the back sight reading to the elevation of the point on the ground to get the HI. The foresights are always subtracted, so they're sometimes called minus sights. So what you do is you take the HI, the height of the instrument, subtract off the foresight, and you'll get the elevation of the point on the ground. So it's just basic addition and subtraction to work through the notes. So there's a set of notes that correspond to this level here, this level loop. So what we do here is we put columns. Station is the point where you are. Back sight comes next. That's a plus sight. HI is the height of the instrument. Foresight is a minus sight, and then elevation. So we write down the elevation of benchmark M. That's written down right across from benchmark M. So the station goes here on the left, the elevation on the right. Write down the first back sight. Now notice I'm using a notation there that surveyors sometimes use, that 1 with an underline 33. What that means is 1.33. You could write it out either way. It doesn't matter. That's just a way surveyors do that sometimes. Same difference. Okay. So you can take 153.18 plus 1.33. You'll get 154.51. That's the height of the telescope. Okay. So that's the height of the telescope right there. The height of the instrument. Okay. HI, height of instrument. Then you can take the foresight. In this case, 8.37, right there. And you subtract that from the height of the instrument, and you'll get the next elevation of the point on the ground, 146.14. That's called a turning point because you turn the rod on it as you move the instrument from one side to the other. So the elevation of turning point 1 is 146.14. Okay, that's a point on the ground. And then you just repeat that process. So you move the instrument ahead, look back, get 0.22, add that to 146.14, you get 146.36. Move the rod ahead and shoot that. You'll subtract this rod height from the HI, so 146.36 minus 791 is 138.45. That's the point on the ground. That's the elevation of turning point 2, etc., etc. So you work your way through the loop, and you finally do what's called closing, which means you get to a point of known elevation, your last point on your level loop, and we measure it at 145.14. Okay, now notice that the actual elevation of that point is known to be 145.11. So we have some error in the survey, which is a common thing when you do surveys. The purpose of this particular survey was to set benchmark P, which was marked with a 5/8 inch iron rod. So that was the purpose of this survey, to set this point on the ground right here, which is going to be a new benchmark apparently. All right, now we do some standard things here. The first thing we want to do is check our arithmetic. So to do that, you add up all the back sites and get the sum of the back sites, which in this case is 40.24, and then add up all the fore sites, which in this case is 48.28. Then to check your arithmetic, you take your first elevation, the 153.18, add the sum of the back sites and subtract the sum of the fore sites, and we end up with 145.14, which is what we calculated when we kept the notes here. So that's okay. That's a check on our arithmetic. The next thing we want to do is get the error of closure. Okay, we got 145.14. We know the elevation of that benchmark we closed to is 145.11. So if we take 145.14 minus 145.11, we get 0.03. That's the error of closure. We came in 0.03 feet, 3/100ths of a foot too high. We can then check and see if that's acceptable error, and there's many ways to do that. For construction surveying, the way you do that is you take 0.02 times the square root of the number of setups, okay, which in our case would be 7, because we have 7 HIs. 1, 2, 3, 4, 5, 6, 7. Okay, and when we get that, we get 0.05. I rounded to that. That's greater than our error of closure, the 0.03. So we're okay. We're within acceptable error. But we still want to correct the error. So to do that, we take the negative of our error of closure, because we came in high, had a positive error of closure. We want to correct down. So we take negative 0.03 and divide it by the number of setups, which is 7, and we get negative 0.0043. All right, the next thing I want to do is get the adjusted elevations that correct for the error, okay? So I'm going to take the elevations I got from my original set of notes, and then I'm going to adjust them. I take my correction factor and successively multiply it by 0, 1, 2, 3, 4, 5, 6, and 7, and adjust each of those elevations by those products. So the first elevation is 153.18. Well, that doesn't change. That's a benchmark, okay? That elevation will stay at its known value, so 153.18. The next elevation I'll adjust by 1 times my correction factor, negative 0.0043. Well, that works out to be negative 0.0043, but I only shot this level loop to the 100th of a foot. So I'll round that correction to the nearest 100th, which in this case is 0. So that next elevation will stay at 146.14 because the total correction is just rounds out to 0. Now the next shot, I'll take 2 times the correction factor, negative 0.0043. I'll get negative 0.0086. That rounds out to 100th. So I'll drop this elevation, subtract off that 100th, and get my adjusted elevation of 138.44. 3 times the correction factor gets me negative 0.0129. That rounds out to 100th, so I'll subtract 100th from this elevation. And I'll just keep going with that procedure, okay? Now, my very last shot, when I take 7 times negative 0.0043, that should come out to be the negative 0.03 that will exactly correct my closure here. So when I take my elevation that I got, 145.14, subtract off this value, that should come out to be the known value of benchmark R. That's kind of the target that I'm trying to adjust to. All right, so that's the basic procedure for working through level nodes, level loop nodes. Now, I like to write up my notes where I kind of snake my way down the page. So each successive reading and calculation I do is just a little bit lower than the one before. That way I can tell what order to do the arithmetic. Now, an actual surveyor in practice would set up the notes like this in what I call a more compressed form. Now, you leave the first foresight space blank and start the first foresight on the second row. So here the pattern that you're working through is something like that. Okay. And that's how you're working through that. It's just a more compressed form. Even when I've worked in industry, I still write notes like this because it's just easier and simpler for me to read. So you could do it either way. If you do compress your notes, as I'm showing here, be sure that you leave in that first row the foresight space blank and move that first foresight down to the second row. That's how that would be done in industry. All right, so that's just a little bit of a review on level loop nodes.